So in the last lecture, when we were discussing the concept of the potential, I looked at a very interesting idea due to Lorentz. What Lorentz did was to look at the energy, the electrostatic energy in a spherical charge distribution. So what is it that I have? I have a charge density rho in a sphere of radius r. We computed that in the previous lecture and we found that the electrostatic energy is given by 3 over 20 pi epsilon naught q squared by r, where r is the radius of the sphere. So we are imagining that there is a certain material of a certain radius r in which the total charge q is uniformly distributed. That is how we wrote this expression. Rho is a constant, and in the previous lecture we derived the expression that the electrostatic energy is given by this quantity 3 over 20 pi epsilon naught q squared by r. Now, during the time of Lorentz, the only elementary particle that was known was the electron, and people believed that all kinds of charges will be built out of the electron. Of course, there is the nucleus which is made of the proton and things like that. We do not have to worry about that. Let us concentrate on the electron. So, what Lorentz did was to argue that if I consider my object to be not any object but an electron, then we know that my electron also has a mass which is given by 0.511 MeV by c squared. But on the other hand, from relativity, we know that associated with every energy there is a certain mass. I shall call it as the electromagnetic mass because I am looking at the electrostatic energy. Therefore, it is the electrostatic mass which is nothing but MEL into c squared. Therefore, I have another kind of mass, the electrostatic mass, which is given by UEL by c squared. The question, the important question that Lorentz asked was, why should the inertial mass given by 0.5 MeV by c squared be different from the electromagnetic mass? After all, if I subject my electron to an external field, my electron moves. As it moves, the whole charge moves. Therefore, my electrostatic energy also moves along with it. Therefore, Lorentz found it very tempting to identify ME, the standard inertial mass of the electron, with the electromagnetic mass which is given by 0.5 MeV by c squared. This was indeed the temptation that Lorentz had, and therefore Lorentz postulated that perhaps all the mass of the electron is because of the charge distribution over a certain radius r, in a sphere of a certain radius r. Now, this is indeed a very bold physics, and as I said, it is a stroke of genius because now we are actually trying to derive the mechanical properties of an object through its electromagnetic properties. This is a very, very bold concept. So, let us go back and look at what the meaning of this identification is. If you look at the electrostatic energy, I know the charge of the electron, the value of the epsilon naught is fixed, and on the other hand, if you look at the inertial mass, the mass is known 0.5 MeV by c squared. Therefore, the only free parameter is the radius of the electron. R is the free parameter in the U electrostatic, and that gets fixed by identifying my M electrostatic with the M inertial. So, this is indeed what Lorentz did. Now, we know all the values. I invite you people to pick up your paper and pencil and plug it in. If you did that, you will find that R electromagnetic or electrostatic, let me call it, turns out to be of the order of 10 to the power of minus 15 meters. So, if indeed the mass of the electron arose because of the electrostatic energy of the electron, it is a different matter as to how these charges are held together. Let us not ask ourselves that question. Then my electron should carry a radius of 10 to the power of minus 15 meters, of around 10 to the power of minus 15 meters. Our considerations are completely classical, therefore it is also called the classical radius. The classical radius of the electron. Classical electromagnetic radius of the electron, that is what we should call. If it is correct, then I should be able to perform an independent measurement and then measure the radius independently and ask whether it agrees with 10 to the power of minus 15 meters. Therefore, the question is, what is the radius of the electron? What do experiments tell us? Tell us. The answer to that comes from the so-called scattering measurements, and I think I already told you at the beginning of this course. Let me repeat. We know that the radius of the electron is known to be less than 10 to the power of minus 19 meters. Please notice that 10 to the power of minus 19 meters is the upper limit on the radius of the electron. What is the statement that we are making? If at all the electron has a radius, it has to be less than 10 to the power of minus 19. Perhaps it is 10 to the power of minus 20. Perhaps it is 10 to the power of minus 30. Perhaps it is 0. In fact, all known experiments today which have probed lengths to very short distances tell us that it is convenient to assume that my electron is a point particle. However, if you look at the expression for U electrostatic, we find that the energy goes like 1 over R, that is, the electrostatic energy of the charge distribution increases indefinitely. It diverges like 1 over R, though therefore as R goes to 0, U electron goes to infinity. This is a major problem, and it clearly tells us that the naive idea of Lorentz is not going to work. If this idea is not going to work, why is it then I said that Lorentz had a stroke of genius? It was an act of genius. To get a complete answer to this question, you will have to wait for a while. In the second part of the course, you people will study a little bit of modern physics, a little bit of quantum mechanics, and one thing that you people will realize is that this so-called classical radius of the electron demarcates two different regimes. If you are looking at physics in lengths greater than 10 to the power of minus 15 meter, you can actually use classical mechanics as far as the dynamics of the electron is concerned. But if you are looking at phenomena less than 10 to the power of minus 15 meter, then you should use quantum mechanics. Therefore, although this idea might not have worked out, this idea is not useless. In fact, it is quite useful, provided we combine this idea with ideas of modern physics, namely quantum mechanics. So this is something that we learnt by a little bit of extrapolation from our standard electrostatics. Before I conclude my discussion, I am tempted to work out two more examples. I will not work out the problems completely. I will indicate to you as to how to solve the problem, but I would urge all of you to solve both these problems because they will gain experience in finding out the interaction energy, and also these are interesting problems from the viewpoint of electrostatics. Now, so far I looked at two concentric circles or spherical distributions or a single spherical distribution. Now let me look at another case where I have one spherical distribution of charge here. So this has radius R1 and the charge density is ρ1. This is my system 1. Now at a certain distance I have another spherical charge distribution. Now this spherical charge distribution has a radius R2. There is a density ρ2 which is sitting here. The two spheres are displaced with respect to each other. Now earlier one sphere was enveloping the other sphere. When I looked at the surface charge densities, now they are displaced with respect to each other and there is no overlap of the charge densities. And if I were to draw a line connecting the two centers, the distance between the two centers is given by R. So how many length scales are there? The radius of the sphere 1, that is R1, the radius of sphere 2, that is R2, the distance between the two centers R. These are the three length scales that I have, and of course I have the ρ1 and I have the ρ2. Now I ask myself what the interaction energy between these two spherical charge distributions is. This problem is not without interest if you remember what Newton had to do in the similar context of gravitation. Newton could not straight away make use of the idea that the sun can be treated as a point particle, because for a long time he could not prove that the potential produced by a spherical distribution is the same as the potential produced by a point mass, all concentrated at the center of the sphere, so long as we look at the points outside the sphere. Today we are able to prove it in a jiffy, in a minute, by making use of Gauss's law. But Newton did not possess Gauss's law, therefore he had to invent methods, integral calculus, in order to explicitly evaluate it, and historians tell us that it took him more than 20 years to prove that result, and he postponed the publication of Principia Mathematica by that many years. Now what we are doing is to slightly complicate that problem. We are not looking at a point mass moving in the field of a spherical charge distribution. In the case of gravitation, it would have been spherical mass distribution. Mind you, in planetary motion we assume the planets to be a point mass. Here we are looking at two spherical charge distributions, two spherical distributions, and we are not making any assumption on the values of R1 and R2, and I am asking, is it possible for me to compute the interaction energy? Now I know one thing, that dimensionally my energy should look like Q squared over L. So Q squared, that means it should look like Q1 Q2 divided by L, except that there are three length scales, R1, R2 and R, and how are we going to argue what kind of a combination of R1, R2 and R are going to contribute to this my L. So what we are interested is in the dimensional analysis. That is what we are trying to do. However, a little bit of thought tells you that this problem is in fact very simple, except that in order to perform this integration, do not look at the field, do not look at the charge densities, but write the expression, my U is simply given by integral rho, let me say 2 of R2, this is what I have, then phi 1 of R2 divided by mod R1 minus R2 d cubed R2. So I am writing the interaction energy. So perhaps I should change my symbol here. What I will do is I will replace U by U12. That is what I shall do. Now because my charge distribution 1 is a spherical charge distribution, I know that the potential produced by this charge distribution is as if all the charge were concentrated at the origin. In other words, phi 1 of R2 is independent of R1. If phi 1 of R2 is independent of the radius R1, that means if at all this U12 has to depend on some parameter, it has to depend on the distance R and the radius R2. But then we know that this expression is symmetric between the potential and the charge distribution. Therefore, let me write one more expression now. I will say my U12 is simply given by integral d cubed R1. Now I will integrate over the first charge distribution which I had written around the origin. Now I will write rho 1 of R1 phi 2 of R1 divided by mod R1 minus R2. This is the equivalent expression. So we are calculating the potential coming from the second spherical charge distribution which was displaced with respect to the first one, and we are asking ourselves the question what it is. Again we will find that this expression is independent of R2. My previous expression told me that it is independent of R1. This expression is telling me is independent of R2, and therefore I conclude that my U12 must be simply 1 over 4 pi epsilon naught Q1 Q2 divided by R. Of course, this is not the end of the story, and some number which I shall denote it as K, which is yet undetermined. So except for an overall multiplying factor, we have been able to write down the potential energy between two spherical charge distributions. it is exactly the same as the potential energy of 2 point masses except an undetermined k. Undetermined k value. Now, it is a pretty simple matter to determine the value of k, because we know k cannot depend on R1, R2 or R. All the dependencies have been exhausted. Therefore, we shall take the limiting case when R1 goes to 0, R2 goes to 0. When both of them goes to 0, we know that U12 goes to 1 over 4 pi epsilon naught Q1 Q2 by R. But then this should come as a limit of this particular case. This implies k is equal to 1. So, by intelligently making use of Gauss's law and the fact that I have two spherical charge distributions, we have found that the potential energy of two spherical charge distributions is exactly the same as an equivalent potential energy of the charges concentrated at the centers of the respective spheres. This argument would of course hold even in the case of gravitation. Therefore, if you take Earth to be completely spherical, if you take Sun to be exactly spherical, then all that you need to know is what? The distance between the centers of the Sun and the center of the Earth, and that will simply give you the interaction energy, so long as we can ignore, we can neglect the rotational motion either of the Sun or of the Earth. So, this is an interesting lesson that we have learnt. Now, what I would like you people is to actually convince yourself that my previous argument was right by doing an explicit calculation. Is that okay? That calculation is not difficult to perform. All that you have to do is the simple integration. There are similar integrations which are found in books like Griffiths. You may look them up and I would like you to do that. So, let me give you the problem. The problem for you is that verify the result that U12 is nothing but Q1 Q2 over 4 pi epsilon naught R by explicit calculation. Okay? That will give you some experience. So, let me give you this problem and then go to the final example before I go on to discuss certain interesting aspects of electrostatics. The next problem is quite interesting. What I will now do is to again consider a sphere and make a distinction between the upper hemisphere and the lower hemisphere. So, here is the last example which I am working, maybe example 3 if I remember right. What we shall do is to paste a uniform surface charge density sigma 1 on the upper hemisphere and a uniform surface charge density sigma 2 on the lower hemisphere. Okay? Now, the way I have done this, I have constructed a sphere, looked at the equatorial plane, there is a sigma 1 on the upper hemisphere, there is a surface charge density sigma 2 on the lower hemisphere. And in order to make my life simple, if you want, although it is not necessary for calculation, you can choose sigma 1 equal to minus sigma 2 equal to sigma. Sigma can be taken to be greater than 0. So, obviously, what is the question of interest for me? The question of interest for me is the interaction energy, the potential energy between the upper hemisphere and the lower hemisphere. Now, this is an interesting example in integration using spherical polar coordinates. So, let me write down the expression for you, but I will not work out all the steps. I will ask you to fill in the gap. So, how does the expression look like? In order to evaluate this expression, I will now employ the expression for the energy as given in terms of the two charge densities. So, mind you, what have I done? In one case, I looked at the expression for the field E1 dot E2. In another case, I looked at the expression in terms of the charge density and the potential. Now, I am using the third equivalent form, namely the interaction energy written in terms of the two charge densities, and that is nothing but 1 over 4 pi epsilon naught integral d cubed r1 d cubed r2 mod r1 minus r2 is what I have, rho 1 of r1, rho 2 of r2. Rho 1 of r1 corresponds to a charge density on the upper hemisphere, rho 2 of r2 corresponds to the charge densities on the lower hemisphere. Mod r1 minus r2 gives you the distance between a charge distribution in the upper hemisphere and the charge distribution in the lower hemisphere, and we would like to evaluate that. Now, the first exercise that you have to do is to learn to write my surface charge density in terms of the volume charge density. So, you people should convince yourself that this expression is nothing but 1 over 4 pi epsilon naught into, I am not interested in what? The volume charge density, but the surface charge density. Therefore, I will write ds1 ds2. These are indeed what? The surface elements. Then I have mod r1 minus r2 into sigma 1 into sigma 2. I have taken sigma 1 to be constant and sigma 2 to be constant. Therefore, I have a ds1 ds2 mod r1 minus r2. This is my expression for the energy, and you people should convince yourselves that it has the right dimension. Sigma 1 ds1 gives you one charge, sigma 2 ds2 gives you another charge. Therefore, it has the dimension of q1 q2 by r with the factor 1 over 4 pi epsilon naught, and that is indeed the correct expression. Now, since sigma 1 and sigma 2 are constants, and since we have said that it is equal charge, actually it need not be at this particular point. How do I write that? Let me bring it out as the first step. I will write it as sigma 1 sigma 2 over 4 pi epsilon naught, and now we are going to write the expression for ds1 and ds2. If my sphere has a radius r, obviously I am going to get a factor 2 pi r whole square. Let us understand where it comes from. The factor 2 pi comes from an integration over the phi degree of freedom, and the surface element is what? R squared d omega, and d omega is sin theta d theta d phi. So, let me write that ds1 is nothing but r squared sin theta d theta d phi. I perform an integration over d phi, I will get a 2 pi. 2 pi r squared is what I am going to get, and then I will get another 2 pi r squared. So, that together will give me 2 pi r squared whole squared, and this is this expression. Okay. Now, we are left with the integration over sin theta 1 sin theta 2. So, let me write it here. Sin theta 1 sin theta 2 d theta 1 d theta 2 is what I have, and I have to write my expression for r, and you people can convince yourselves that this expression mod r1 minus r2 is nothing but r mod cos theta 1 minus cos theta 2. So, I am employing my spherical polar coordinate system here. So, if I have a point P, x, y, z, this angle theta is what the radius vector makes with respect to the z-axis. That is what I have. The only thing that I have to be careful is to fix the range for the integration theta 1 and theta 2. Notice on the upper hemisphere theta 1 will go from 0 to pi. 0 less than theta 1 less than pi by 2 is the range for theta 1. Pi by 2 less than theta 2 less than pi is the range for theta 2. You have a cos theta here, you have a sin theta d theta, and sin theta d theta is nothing but d of cos theta. Therefore, what I invite you people to do is to integrate this expression. If you integrate this expression, you people can see that you will get an expression dt1 dt2 divided by t1 minus t2. Therefore, how does your expression for the charge look like? The expression for the energy density will roughly look like, let me give you the answer. I will get a q1, q2, 4 pi epsilon naught with a 1 over r, some number of the order of 1 and a number of the log 2 into some constant. So, what I ask you people is to determine this value of this constant. Determine the value of this constant. So, this is the next problem for you. And remember this result, because this can be used to actually determine other quantities at a later stage if I make it into a conductor or some such thing, although it would not be entirely correct to do that. So let me leave it as the last example, last problem for you in terms of the potentials, and now what I shall do is to go on to study other properties, the real properties of real materials. So in some sense, all this time I have been looking at what I will call as textbook problems or problems of academic interest. However, the big question that arises is, where is electrostatics important for me in real life? We know that electrostatics phenomena were first discovered probably thousands of years ago, when one of the ladies was combing her hair, or when somebody rubbed amber against something else. But today, are these electrostatic phenomena merely of some interest because it is there in our syllabus, or do they have any practical significance? That is a question that we have to ask ourselves. The answer to that is provided by looking around everyday phenomena, and one thing we should know is that modern civilization today is dominated by electromagnetics. In fact, apparently when Faraday found induction law, discovered his famous induction law, it tells you that whenever there is a changing magnetic flux, there is a corresponding induced EMF. Some politician asked him, what is the use? And Faraday told him, as of today I don't know what its use is, but let me assure you, you are certainly going to collect taxes based on that. In a similar manner, we have to ask ourselves, okay, Coulomb gave us the Coulomb law. We have been able to write it in a very sophisticated form, divergence E equal to rho by epsilon naught, curl of E equal to 0. But what is the impact? What is the import of these electrostatic phenomena on our daily life, for better or for worse? The answer to this question actually goes back to first of all trying to asking the question, what kind of charges can be carried by various objects? If I am going to say that, look here, I charged a body and 2 electrons sat on it or 3 electrons sat on it, that is not of much use. We should first of all ask ourselves what kind of a voltage is developed when I produce, for example, electrostatic charge distribution by friction or some other means. Therefore, first of all, let us look at real life examples of what kinds of voltage are produced, and then go on to ask what kind of effect they can have. That is indeed the proper way of looking at all these things. So let me start looking at some of the examples. Okay. So the first example is constructed in this particular table, and let me look at the first example. What I want is this example, and the most important that we have to notice is that electrostatic phenomena in everyday life involve very, very high voltages. We have 5 volt batteries and we connect 2 of them or 3 of them and we perform experiments. No, that is not the kind of voltage that we are interested in. And here is a table which tells you the kind of charge and the kind of voltage that you can pick up. Of course, it depends on a variety of conditions, what kind of a dress you are wearing, what kind of shoes you are wearing, the kind of surface on which you are walking, what kind of a humidity it is. And look at this table. This table tells us that if you walk across a carpet and if there is very little humidity, what is the humidity? Relative humidity, the humidity in the atmosphere as far as we are concerned, you can pick up an enormous voltage, a voltage as large as 10 to 35,000 volts, which is not a small volt at all. If you look at AC voltage source, it is 230 volts. That is what we have. You can pick up an enormous voltage. However, if you are lucky that the atmosphere has lot of humidity, imagine that it is a rainy day, or you are in a coastal area where there is always a lot of humidity, then the humid air will take away a lot of charge from you. It will be down by many orders of magnitude, because it is almost 10 orders of magnitude, and it will turn out to be 1500 volts. This is walking on a carpet. This is a highly insulating material, and when you walk, there is a friction between your shoes and the carpet that causes a charge transfer. If you decide not to work on a carpet but on a modern house, in modern houses we put vinyl tiles all over the place because we want our houses to look very nice. If you did that, you won't pick up something like 35,000 volts, but you will pick up something like 12,000 volts. What about a worker at a bench? A worker at a bench will be hammering, will be working on a lathe, or he might be doing carpentry. Again, there is a lot of friction, and experts who have made measurements say that you can pick up actually voltage up to 6,000 volts. If you are working and if there is some polythene bag which is a very good insulator, and you see that if you did that, a voltage can be as large as 20,000 volts. And of course, we all have our modern chairs. We don't sit on Godrej chairs or wooden chairs. We have these urethane foam chairs, right? Nice fancy chairs which companies like Godrej make. You can again pick up a volt like 18,000 volts. So, seemingly innocuous actions on our part seem to be producing voltages of enormous values, all the way going from something like 6,000 volts to 18,000 volts. As I told you, if the humidity is very large, it goes down correspondingly, but please notice that even these numbers 1500, 250, 100, 1200, 1500 are not small numbers, therefore we have to treat them with respect. So imagine that I have actually walked along a carpet or picked up a poly bag or rubbed myself against something else. This way of transferring the charge is what is called as Tribo Electricity. Tribo is a word which is used for friction. By friction I have been able to transfer the charge, is that okay? And now I ask, I go and try to switch on an electronic equipment, I sit in front of a computer, or I open the computer and look at the lead which is connecting to my hard disk, etc. And I ask how much of voltage can actually be taken up by these materials. If the threshold voltage at which they work is much smaller than the voltage carried by me, the minute I discharge that much electricity to those equipment, they may break. So again, this electrostatic discharge sensitivity has been shown in these tables. The first table tells you the sensitivity up to 0 to 1000 volts. And mind you, these are devices which are used in everyday life. The first one gives you microwave devices. The second one is MOSFET, which you people will encounter in your laboratory. Then you have CCDs, charge coupled devices, which are used everywhere. Operational amplifiers, which are all pervading in your electronics, laser diodes. And look at this, you have the GMR disk, driving record heads, which are there in your computers. So you better be careful to discharge all your voltage before you touch the sensitive equipment. And mind you, these voltages are not too large, because I told you that you can pick up as much as 20,000 volts, 30,000 volts by simply walking. In fact, you don't even have to look at these examples. If you are an active person, you can give a shock to another person also. That's a different matter altogether. There are also devices which are slightly higher than this. So, for example, you have again certain integrated circuits, hybrids, transistors, etc., which have a sensitivity level up to 4000 volts. Is that okay? Therefore, all the way from 0 to 4000 volts, we have a large number of, a plethora of, a surfeit of electronic equipment which can break down. Experts who study this, in fact, there are whole organizations called what? Electrostatic discharge societies. There are journals devoted to that. You can go to internet and you can find out, or you should go and ask one of your teachers who may be working in this area. They tell us that we should be very careful in handling these equipment because they may break down, and there are two kinds of breakdown apparently. One is called catastrophic breakdown. Catastrophic breakdown, where the breakdown takes place immediately. So I charge myself and I try to open up my computer or some other electronic equipment, my hi-fi system, it breaks, I may be blaming my manufacturer. Actually, the culprit may be my walking on the carpet. So we should be very careful before we blame the manufacturer. If it breaks down immediately, it is called catastrophic breakdown. Here, the breakdown is immediate. But on the other hand, the more dangerous, the more subtle thing, where it is not easy to trace the origin, is what is called the latent breakdown. In the latent breakdown, what happens is that there is not a complete breakdown, but the efficiency of your component goes down, and then after repeated such usages, one day it will break down, and that day you might think, look here, this was a perfectly humid day, I did not carry any charge, then in spite of it, it broke down. Therefore, it might be the manufacturer's mistake. No, please be careful. There might be a latent breakdown, and that can also be caused by this equipment. Indeed, if the user can cause a breakdown, perhaps breakdown take place at all levels. When there is a manufacturer, when it goes to the contractor, when it is packaging and things like that. And here is a table which the engineering experts have actually compiled. You see that the component manufacturers themselves spoil their equipment, sometimes up to 97%. On an average, 20% of what the manufacturer manufactures is lost to us because of the electrostatic discharge. Then there are subcontractors who buy this equipment and assemble them, like various computer firms that we have in our country. There, the loss goes from 3% to 70% with a mean of about 9 to 15%. Then there are contractors who probably package them and all that. There, the mean breakage is up to about 8 to 14%. And the users are there who can cause a loss from 5% to 70% with a mean of 27 to 33%. So what is the lesson that we have learned? The lesson that we have learnt is electrostatic discharge is of nuisance value. Is that part okay? At least so far what we are seeing is that it is of nuisance value. So we started with a glorious subject called electrostatics. We did lot of vector analysis, vector algebra. We wrote it in a sophisticated form only to conclude that it is acting as a nuisance trying to spoil my equipment. Is it indeed so? The answer is no. If the electrostatic discharge has a flop side, it also has a flip side. And where does the flip side occur? Here is a representative picture which shows you how electrostatic discharge can actually be used, and one is in the separation of the materials. If I have an anode and a cathode, which I have shown here, there is a high voltage so-called corona wire which causes a voltage difference between the two plates. Then the voltage difference that I create between the two plates can actually be used to separate material. The figure on the right hand side tells you how to actually purify your air. My air can have lot of ions which carry a charge, and it is not very good for us to inhale this ionized gas. So what we have to do is to actually neutralize, trap all the ions and get the neutral air. Where does it occur? In factories, for example, where a lot of production is taking place in open air equipment, the air can get ionized. It is essential to purify the air before it is let out, and that is where the separators are useful. Or for that matter, if you look at your stove in your house, it produces soot. Of course, there is a steam, there is a smoke that is coming out, it carries a lot of soot, that will be ionized. And what do? Nowadays you put sophisticated chimneys which attract all those soot. That also uses the principle of electrostatic discharge. Because the soot is ionized, it goes and settles onto the metal plate which is at a certain potential, attractive potential. Now, there are many materials which we would like to separate. Asbestos might be mixed with silicates. This is one particular example. Fly ash may be mixed with carbon. We know that fly ash is made use of in making very good cement nowadays in thermoelectric plants. Then, of course, all of us have to live and all of us have to eat in order to live. I may have to separate barley and rice from rodent excrement. Rodent excrement is there because of the pests, and that is very bad for the health. Nobody wants to eat them. Or I might like to separate cocoa beans from the shells. Cocoa beans are used for making chocolates, which we all like. I might like to separate grain from garlic seed, so on and so forth. Or photographic film from paper, polyvinyl from polyester. All these can be done by using the separation method. Not only that, earlier you see that people, whenever they wanted to paint surfaces, the painter will take a brush and paint it. But nowadays we have what is called as a spray painting. Or if you look at your chairs, or if you look at your trays in your house, in your microwave or your baking oven, they are all powder coated. What is the principle behind microwave coating, this powder coating or the spray coating? The spray painting and the powder coating are again based on the electrostatic voltage difference. What is the great advantage in this? The great advantage in this is that electrostatic forces are stronger than gravitation. So, suppose I have a plate here and there is a spray gun which is sending the paint. If I am holding it like and painting it, I can ignore the effect of the gravitational force because the electrostatic force is much stronger. The electrostatic attraction is much stronger. So what is the principle behind this spray painting or the powder coating? Let me list them. The first thing is that electrostatic force dominates over gravitation. So I have a plate which has to be powder coated or painted. I hold it as a certain voltage, and if I have a gun and if I spray it, the effect of gravitation is negligible, and so long as this is uniform, the coating is also uniform. Secondly, the voltage difference that I apply is easily measurable. Unlike gravitational force, which is very weak, this is easily measurable. So dominates over gravitation. Number 2, electrostatic force is easily controlled and measured. That is the next advantage. And the third one is, I am sending this in the air, does it affect the air motion? The air motion is barely affected. So that we are not affecting the environment. All these go to make it into a plus point, and therefore you see, you want to separate, you want to coat, you want to paint. All these situations, it is much better to use the electrostatic principles rather than the old brush and the paint. So to summarize my discussion of the impact of electrostatic forces on our modern day life, for better or for worse, it has a dominant role. As I told you, we are living in a sea of electromagnetic phenomena, of which electrostatic phenomena are also a part. Therefore, if we are careful, if we are wise, if we are intelligent, then we should actually be able to make use of electrostatic phenomena to our advantage rather than to our disadvantage. This brings us to the next question as to how I actually employ electrostatic phenomena to my advantage. You see, I made a statement that if I were to walk on the carpet, I pick up a voltage of up to 35,000 volts. Who walks on the carpet? Now, there is a great distinction between a child walking on a carpet, or a dog walking on a carpet, or a fully grown person walking on the carpet. What kind of a shoe am I wearing, and what kind of a humidity is, etc., etc. In other words, whereas all these time we imagined charges to be abstract and are given at will because we wanted to solve a few textbook problems, now we have to actually study properties of the materials. So now what I am going to do is to start a new topic. Let us remember, we want to start this new topic because we want to understand electromagnetic phenomena in media. So this I shall call as electrostatics in media. A subject which was again started by Maxwell and sort of put on a very firm footing by Lorentz. Is that okay? That is what we want to study and ask how certain objects respond in a certain way to external environment consisting of the electric fields. So what am I trying to say? Now my purpose is more ambitious. I am not interested in the Coulomb law anymore only in free space. I am also interested in Coulomb law in a medium. So imagine that I have a parallel plate capacitor. So I have two plates. This carries a surface charge density sigma. This carries a surface charge density minus sigma, and it produces an electric field. It produces a uniform electric field. And Gauss's law tells us that my electric field is simply given by sigma by epsilon naught. Is that right? Sigma by epsilon naught is what we are going to get. That is what Gauss's law tells us. And of course, if I call this as the direction n, this is what it is. Now the kind of question that we want to ask is, suppose I put a jar of water containing in this. So I put my water in this. What is the electric field here? in the jar of water. Or perhaps wood, or perhaps mica, or perhaps a metal. Is that okay? Or perhaps a very something like a superconductor. So now you see I am using many words. I use the word like metal, I use the word like superconductor. So in short, the question that we are asking is, how do different materials respond to external electric fields, and how do they modify because of that response the field within and the field without, and that goes by the subject matter of electrostatics in media. This indeed is an extraordinarily important subject for all of engineering. So I am going to go very slowly, very carefully. Let us take some time. But before we do that, before we try to ask questions like what is the electric field or what is the magnetic field in the presence of media, we have to make a fundamental distinction between what I call as a microscopic field and a macroscopic field. In fact, I have a suspicion that the next 15-20 minutes or so will be taken up by this discussion, but never mind, let us go around slowly because this is important. So let us try to understand the distinction between microscopic and macroscopic fields. And those of you who have been following all the lectures will remember that sometime in the 5th or the 6th lecture, I evolved a procedure. I taught you how to average over charge densities. That is indeed the concept that I am going to introduce at this particular point. So in order to make my example concrete, let me consider a material like wood or a material like glass. We know glass is overall neutral. Glass is overall neutral. So take a piece of glass and bring an electroscope near that, it is not going to respond. That is what we have. However, what is glass made of? Glass is made up of a large number of atoms, and all these atoms are bound by electromagnetic interactions. So although this is neutral, these are held together by electrostatic interactions. So what do I have? If I consider any material, there are the positive nuclei, positively charged nuclei, which they won't move, and there are electrons orbiting around. They form an atom. One atom interacts with the next atom, they get bound together, and that is how these are held. Therefore, if I were to try to draw a profile of an electric field, how would it look like? So let me make a cartoon of a picture and show how it looks like. So imagine that there is an atom, and at the center there is a nucleus and there is an electron, and let me imagine that I am going to ignore the field due to the positively charged nucleus. Let me concentrate only on the field due to the electron. So as I approach the electron, my field goes to negative infinity. Is that right? Very close, it goes to negative infinity. As I go up, it goes to 0. As I go farther away, it again blows up, again it goes up. Therefore, this is the kind of figure that we are going to get. So it fluctuates to very large value. If you feel like this is something of a logarithmic scale, this is my electric field, and over atomic distances my field is going to change. This is a snapshot at a given time. However, we know that my electrons are not at rest. They are going round and round the positive nucleus. At the next instant, the atom is in a different position. So in the next instant, probably I can use a different color. How will it look like? It may look like this. This is the next snapshot. So this is at t equal to t1, okay, and this is at t equal to t2. So as a function of time, my electric field profile is changing. As a function of space, my electric field profile is changing. Now the natural question to ask is, what is the length scale here and what is the time scale? This is t equal to t1, what is t equal to t2, what is delta t equal to t1 minus t2 equal to what? What decides the scales? The answer to that is very clear. The length scale is given by the molecular separation, atomic or the molecular separation, whereas the time scale is given by the periods of the electrons. Let me write it down. The length scales over which E fluctuates, the electric field fluctuates, let me call it delta L, is of the order of molecular separation. Okay. If I look at the length scales, time scales, then they are of the order of the period of revolution of the electrons. Electron revolution. So these are of a few tens of angstroms. These are about 10 to the power of minus 15 seconds or so, extraordinarily small numbers. Now that was only looking at the electron. However, suppose I were to draw the complete picture including the field produced by the nuclei also, which are carrying positively charged. Now what happens is something funny. At any given point, my electron field will behave like this. These are very large fields, whereas the field due to the positively charged particle will look like this. Is that right? It is going to look like this. These are at rest, but these are moving. Therefore, the point is that if I am going to look at these atomic dimensions, I will be able to see this electric field, I will be able to see this electric field, but my electroscope is not sensitive to this. So this is my electric field, that is what I have. This is coming because of the nuclei. This is coming because of the electron. We ask ourselves, what is the mean field? What is the mean field averaged over reasonable distances? Perhaps the tip of my electroscope is of the order of a few microns. Then it is going to measure the average field over a spatial extent of a few microns, and if this is of the order of a few angstroms, tens of angstroms, I am obviously going to ask the mean field in this region. This is highly exaggerated. I am asking what is the mean field in this region. And clearly the answer to that is the mean field will be equal to 0. So what we have found is that the spatial average of my highly fluctuating, very strong electric fields are going to average to 0. That I have to write formally. So let me go back to my original question. I have to make a distinction between the microscopic field and the macroscopic field. Microscopic fields, let me denote it by the lower case. So let me say microscopic field is denoted by E, the small e, and the macroscopic field, it is denoted by capital E. Let me imagine that. So how do I define my macroscopic field E given by the microscopic field E? I will write it to be the spatial average. My E at R is the mean value, is nothing but 1 over volume integral d cubed r prime E of r plus r prime, the radius, into this, where my r prime will go, let us say, over a reasonable volume. R prime will go from r minus r to r plus r. If you want, you can put a factor of 2 also. So what am I trying to indicate here? So this is my volume element. So let me imagine this to be a sphere. What I do is to look at a radius r, calculate the mean value and replace the microscopic field by the value of this. That is what we are saying. So, you integrate over a volume of radius r, find the mean value and replace the microscopic value of this at this point, next move to the next point, move point and so on, and this is my mean field. Clearly, my mean field does not show the wild fluctuations that my electric field was showing. Now, the next thing that we have to know is that suppose I want my electroscope to monitor the time dependence in the field. I cannot say that my electroscope has a sensitivity of 10 to the power of minus 15 seconds. Maybe it can measure over microseconds. Therefore, the next thing that we have to do is to look at E of t, which I will write it as the average over the time. I will write t minus t by 2, t plus t by 2 into E of t plus t prime. I average over an interval t minus t by 2 to t plus t by 2. So, this gives me time average. My previous expression gave me the space average. This gives me the time average. So, studying the bulk properties of the material, trying to write down the Maxwell's equation in the presence of the material tantamounts to replacing the microscopic fields by the macroscopic field. Since I am interested in electrostatics, I have to make one more mandatory statement, and that is the following. When I perform this, I get my macroscopic field all right. What about the magnetic field? We know, although we may not know quantitatively, but at least qualitatively we know that moving charges produce a magnetic field. If I produce a magnetic field by a moving charge, if I average over several periods, then we know what happens to the electron. The electron half the time is moving in the upper circle, half the time it is moving in the lower circle. Then there may be another electron close by which is moving anti-clockwise if this is moving clockwise. Therefore, what we are trying to say is that if I look at the microscopic B of t, which is not equal to 0, the time average B of t, which comes from a similar definition. I shall employ the notation used by the probability people, which comes from the time average of this fellow. This will turn out to be 0. Therefore, in studying the electrostatics of the macroscopic fields, we may safely ignore the magnetic field produced by the moving electrons. If I consider a small physical volume, then roughly equal number of electrons will be moving in clockwise and anti-clockwise direction, and therefore the macroscopic field vanishes both in the time average and in the space average. Therefore, we can forget all about this and say that B identically equal to 0. Before I go on to continue my studies, which will be postponed to the next lecture, let me summarize whatever I am trying to tell you. The study of the properties of matter, electrodynamics in media, involves macroscopic fields E of R. So, if I want to use Gauss's law, curl of E, etc., etc., I am going to apply it to the macroscopic field and not the microscopic field. Therefore, when we are using the macroscopic fields, we want small volumes physically, but large compared to molecular volumes. So, for example, I tell you R going to 0. When I am taking the limit R going to 0, you should understand that I make no distinction between the mathematical 0 plus or minus epsilon, which corresponds to molecular dimensions. So, we should learn to distinguish between an infinitesimal mathematical volume and an infinitesimal physical volume. If you remember this, then electrostatics is not a difficult thing for us to understand, to reconcile with whatever we know from the fundamental Maxwell's equation, and that we shall continue in the next lecture.